Okay, ferritic stainless steels are strong, ductile, can be welded easily, can be hardened but not through heat treatment. Marine application. Okay, martensitic stainless steels. So these have martensite. We didn't talk about martensite above, but when we quench steel, we get acicular or needle-like grains. I'll pause for a second. Okay, so when we rapidly cool austenite, what we get is something called martensite. And martensite, when you have to draw martensite, just draw a whole bunch of sticks, right? If you want to label it, you can say acicular, which means needle-like. What happens is it goes from being a face-centered cubic to a body-centered tetragonal. Now, the likelihood of needing to know that in the HSC is pretty low, but I'm going to put it out there anyway. Okay, so we're going back to when we have martensite, martensitic stainless steel. It's hard, it's strong, it's not as corrosion resistant, but it's used in knives. Okay, austenitic stainless steels. Not as magnetic, can be TIG welded, but with care, right? Because otherwise, if it cools too rapidly, there's enough carbon in it for it to form martensite, and we don't like martensite unless we're going to temper it. Okay, it's ductile and it's formed easily, so it can be used in things like fridges. It's the most common application. 70% of all stainless steels are austenitic. They can be hardened through heat treatment, right? I don't think they can be work hardened very well. Duplex stainless steels. They've got twice the strength. They have medium toughness, so they're between ferritic and austenitic, I think. Good resistance to stress corrosion is their big advantage. Okay, all of these things you can find in the table in the 4th chapter of the book. I've jumped a chapter because I want to talk about all of the ferrous metals at the same time. Okay, precipitation hardening. Now, some stainless steels can be precipitation hardened. Now, this is a bit of a funny concept. Some aluminiums can also be hardened through precipitation hardening. Now, I did not understand this concept until I started teaching it, and a friend of mine who used to live in like Slovenia, he did his PhD in metallurgy, he explained it to me, right? And I said, where does the carbon come from? He's like, well, okay, you know what age hardening is? It's the same thing, except the carbon is already inside the metal, right? It's already like or it doesn't need the carbon from the outside. It's not being pushed into the middle. It's the carbon is already distributed through the whole thing. Okay, so let's have a look at this graph here. Now you're going to complete some stuff. The first step you have to do is do the solutions treatment. Okay, so the solution treatment is this part here and then there. So this is the first step. Yeah? Actually, the first step, it's actually these first two bumps, right? There and there. That's the solution treatment. First of all, you have to anneal. Then you cool before you form. That's fabrication, is the forming. You're going to heat and condition to form austenite. So you're going to form 100% austenite, and then you're going to quench. Okay, so what you're going to produce is you're going to have two grains. So along the grain boundaries, and sometimes between grains, you're going to have a second different phase of material. Now, it depends on what kind of material you're using. This is pretty true of all precipitation hardening. I've taken this image, I've combined this image using the aluminium one, but the idea is we're going to have different grain structures forming along the grains. That's not good. What we want to do is we want to dissolve these little grains, and we want to integrate them evenly throughout the entire network, the entire grain. How I like to think of it is, okay, so the second half of this process is that we are going to age. What we're going to do is we're going to partially reheat. So we don't heat to the same temperature, we're going to partially reheat. And what we're going to do is we're going to allow precipitates to form evenly throughout the entire grain, right? And that strengthens the alloy. The reason why that happens is we have these microscopic, right? Microscopic or submicroscopic, microscopic precipitates. And when we want to try and deform these grains, when we want to try and push grain locations, these little tiny microscopic beta precipitates are going to they're going to push back on that deformation. That's why we get that additional strength. Okay, so that's how that works. Precipitation hardening works. Okay, cast iron. Cast iron is a ferrous metal containing between 2 and 4% carbon. What are its advantages? It's cheap. It casts well. It has vibration dampening. Right? That means that if you have vibrations can actually shake a machine apart. Whereas on the other hand, cast iron often has graphite, and the graphite can absorb those vibrations and dampen the vibration, which can be good for things that are exposed to shock or things that are, possibly could shake themselves apart. They have very good compressive strength, but they're not so great in tensile strength. That's a disadvantage. They can be easily machined. The graphite works well as a good lubricant. So there's lots of if there is graphite, the graphite can provide good machining. They're usually pretty hard, right? So they're usually wear resistant. They're usually pretty durable, right? Now, what does durable mean if it's not hard? You know what? We're going to remove that. We're just going to leave hard. Okay. Downsides, it's brittle, right? You have cast iron, you hit it with a hammer, you've got a better chance of it shattering than if you do with than if you do with steel, right? They usually are not great in tension. Okay, so let's have a look. There are some different elements that we can add. Carbon. Well, if carbon forms cementite, it's going to improve hardness, right? We've seen that as cementite goes up, we get hardness. On the other hand, as graphite increases, right, we're going to improve. So graphite is a form of carbon, right? Graphite is effectively pure carbon. And what some of our cast irons are going to do is they're going to have some parts that are just pure carbon in the form of graphite. Graphite is good because it improves machinability and improves dampening. Silicon, right? What silicon does is I think silicon also improves the flow, but it doesn't say that there. It makes graphite, which improves the machinability, and it helps with the dampening. I'm pretty sure silicon improves flow, but that may only be for cast aluminium. Okay, manganese improves toughness and strength. Sulfur reduces ductility, right? Makes it more brittle. Generally, that's not a good thing, so we want to keep that percentage low. Phosphorus improves fluidity. Now, so if we want to cast something that has very, very fine fins or something very fine detail, we might add phosphorus, and phosphorus really improves the flow when we want to get into very fine areas. Yep, very narrow parts. Okay, there are three main types of cast iron. There's white cast iron. Well, there's white and grey cast iron. There's two kinds of grey cast iron. White grey cast iron, it's not so great. But we're going to use white cast iron later when we need malleable cast iron. So white is good when it needs malleable cast iron. So used to make okay. So limited application means we don't use it very much, but it is used where wear resistance, hardness is needed. Or it's also used to make malleable cast iron, we'll learn about later. Pearlitic grey cast iron has a high silicon content, which makes graphite, which improves machinability and dampening, but reduces tensile strength. So let's look at white cast iron. What we're basically doing is it's just like regular steel, high carbon steel, where what we've got is an increasing amount of cementite. Now, we like a little bit of cementite. A little bit of cementite, we saw, I'm going to go up earlier. A little bit of cementite here gives us a hard, strong steel. But down here, we don't just have a little bit of cementite now. We have this huge chunk of cementite. And cementite is brittle, right? On the other hand, if we add silicon, the silicon takes all of that cementite, it takes all that cementite, takes away all of its carbon, and it makes pure carbon. All of that carbon cementite, yeah, all of that high carbon cementite, it loses all of its carbon, and instead we just have chunks of pure carbon called graphite. Now in this case here, pearlitic grey cast iron, it only has small flakes of cast iron, and the rest of it is pearlite. But we can take out so much carbon, right? So much carbon that we don't even get pearlite anymore. We've gone all the way down. We've gone all the way down to ferrite. Yeah, we've taken out so much carbon that we're back down into the ferrite range. Yeah, I really want to make that point. That does not say cementite, that says ferrite. We've got ferrite grains now with massive, large graphite flakes. Does that make sense? Now, ferrite we know is ductile. Ferrite means it's good for machining. So let's see. Ferritic grey cast iron has good machinability and good ductility. Does that make sense more or less? Yeah? If we have high carbon steel and we just keep going above 2%, we get this white cast iron. It's like super high carbon steel, right? But it's so brittle that it's not really used for much. We use it when we need something really hard. What we can do is we can take out that carbon and just have perlite and graphite. Yeah, that's pretty good. We like perlite, and graphite has some good properties. Graphite is good for vibration resistance or vibration dampening, and it's good for machining. Where we can even take out even more carbon, and we're no longer in the perlite range now. We're now back down into the ferrite range, and what we're going to get is flakes of graphite, which is really good for machining and really good if we need something that's ductile. Now, high-duty cast iron. There are two main types, spheroidal and compacted graphite. Okay, so what we add is we add magnesium and yep.
On our sheet you got low SI.
Yeah, okay, you can change it to this. Yep. Okay, we're gonna have a look. Low silicon, right? Low silicon and high silicon. Yeah.
So we've got 3, you got 2.
Yeah, I know, because these are both spheroidal, right? And I didn't want to break it down, so these are both spheroidal. This is low silicon spheroidal. Remember we said the more silicon we have, the more silicon, the less carbon, or the more silicon, the more graphite. So if we only have a little bit of silicon, we still get perlite. Yeah? If we have lots of silicon, we take out so much carbon that we go all the way down to ferrite. Okay. So what do? We add magnesium or cerium, and we add it just before we cast, and it results in improved tensile strength. It's twice as strong as grey cast iron. It's commonly used in brakes. On the other hand, compacted graphite, we add magnesium, cerium, and titanium. The titanium makes flakes. It's not as strong, but twice the vibration dampening as spheroidal graphite cast iron. But it's only half the vibration dampening of grey cast iron. So it's sort of in between. It's in between having grey cast iron and spheroidal graphite. Okay. Getting to the tail end now, we've got malleable cast iron. Malleable cast iron is produced from white cast iron. What do? We heat treat it and we remove cementite. Okay, we can go black heart. How long do we heat it for? For 2 days. It's soft, it's ductile, it's used in suspension. We have white heart. How long do we heat it for? 100 hours. Right, we heat it for 4 days. Right, we heat it for so long that all the carbon, all of those graphite flakes, they form carbon dioxide and they just leave into the atmosphere. Yeah? We heat it for so long that the carbon forms carbon dioxide and just evaporates. It doesn't evaporate, but it leaves into the atmosphere. What do we use it for? Pipes. Yeah, where we need where we need a cast, but we still need to be ductile. Okay, the last one, pearlitic cast iron. What we do is we make black heart cast iron. We reheat it again. This time the graphite forms perlite. It has the highest strength and it has good wear resistance. Yeah.